Today's webinar, Considering Color in Your Material Property Profile, is brought to you by Proto Labs, the world's fastest source for custom CNC machined and injection molded parts. Your presenter today is Michael Sepe. Michael has worked within the plastic industry since 1975 in various roles involving manufacturing and research and development. He is currently an independent consultant based in Arizona, for which he assists his clients in material selection, design manufacturability, process optimization, troubleshooting, and failure analysis. My name is Jake Godber with ULIDES, and I'll be moderating the event. I'd now like to turn the presentation over to Michael.
Thank you, Jake, and good morning all. I want to start out first of all by talking about what this webinar is not going to be about, because when people see color, a lot of times people come in thinking that we're going to talk very specifically about the chemistry details of color and how to formulate a color for a specific compound. There's plenty of good information out in the literature about that, and the people who do that work for a living know about these things and should be able to guide people away from combinations of colorants and polymers that are inadvisable. So we will not spend any time talking about that, except at one point just to highlight the fact that it is something that needs to be in your thinking. What we want to talk about today is something related to what IDES does for a living, and that is to provide material property profiles for materials. And as we got to talking about what we were going to do with this webinar, the discussion we started getting into was whether or not people understood that when they get a property profile off of the website, do they know that those properties presume the absence of any color, that the properties are assuming a natural material with no modifications from color. And although this is probably something that many of you do know, there are a lot of people out there who do not understand this. And the fact that once color is added, the property profile does change. And it changes in sometimes surprising ways, depending upon the type of color that's being added, the polymer it's being added to, and how much color is needed in order to achieve a certain profile. But the primary thing that people are mostly concerned about when they start adding color is how does the part look? What are the aesthetics? Does the color match? Does it have the right hue? Does it have the right gloss, the right brightness? And very low consideration is given often to what is actually happening to the property profile of the material while all these aesthetic considerations are being given attention to. What I want to start out with is just some considerations for thoughts on color. Molded in color is something we often mention as an advantage of plastics over other materials, metals specifically. Certainly ceramics, wood, all these things have to be painted in order to achieve desired color. And although there are certainly a significant number of plastic parts that still get painted, most notably in the automotive industry, even there, the desire and the target is to get to a point where a Class A finish can be achieved in an as-molded part. So obviously molded in color is going to become more and more of a focus in these industries that consume large amounts of plastic as we go forward, because people do want to get away from painting it. It represents its own environmental concerns and risks. Obtaining the desired color will depend upon the base resin. You start with a base resin, and that base resin has a color itself. And so that's the palette you start with. Colorant formulations now must conform increasingly to a longer and longer list of concerns regarding what we call hazardous substances. The first of these, of course, was RoHS. REACH has certainly come along to add to that list, and this is not going to go away. The list is going to get longer and longer, and there'll be more and more adjustments that have to be made in order to respond to these concerns that are going to be popping up around the globe. And as I mentioned before, the property profile provided in the data sheets assumes no addition of colorant. Now, when we talk about the base resins, we have those materials which are transparent. These are the materials that give us no color of their own to overcome. Things like polycarbonate, acrylic, general purpose polystyrene. These are the materials where we have pretty much the freedom to do almost anything we want. If you look at the line of special effects colorants that are becoming more and more prevalent in the industry, there's plenty of companies that actually have a whole line dedicated to special effects. Very often you'll notice they give a list of materials within which these special effects colorants can be expected to provide the desired appearance. And you'll notice that in many cases that list is short, and it is limited to materials that are transparent, such as polycarbonate and acrylic, precisely because there's so little interference from these base resins in achieving the color. We also can produce the color with relatively low concentrations of color, and this is important because the more color we put in, the more potential there is that we're going to influence the properties of the base resin in a negative way. Then we have base resins with a light translucent color, which are also good candidates for coloring, such as polyethylene and polypropylene. And then we get into things that can be a little more challenging. Dark colors can be difficult to achieve in opaque light-colored resins, and I'll give an example of that. And light colors can be a challenge to create in dark-colored base resins. And if we incorporate a lot of fillers and other modifiers, such as calcium carbonate or talc, which are both white, or impact modification or flame retardants, all of which tend to have that whitish color, then this is going to create some challenges in terms of moving the color in the direction we want to be in from a color aesthetic standpoint. So this is an example of an attempt to do a dark color and a light color base resin. The base resin in this case was an impact modified flame retardant PBT. So we have the PBT providing some kind of a cream color. We have the impact modifier also contributing a whitish color. The flame retardant contributes a whitish color. And the customer says, I want this part to look jet black. So we put in the usual 2% black pigment, carbon black in this case, in order to achieve that black color. And we come up with something that looks decidedly different than jet black. In fact, charcoal gray would be a better description. So at this point, the solution is to just keep adding more color until we finally reach a point where the aesthetics are there. And it took us 4.5% loading to reach the desired aesthetics. When we perform the impact test now on the molded parts, we find out that we've lost the impact performance of the base resin. So we now have a conflict between what people want the part to look like and what they expect to get from the property profile of the material. They obviously selected the material because of its toughness, but the toughness has gone away because of the desire to reach that certain color target. And these are just some of the conflicts that we run into. The light color and a dark color, the case study here is Ultem, polyether amide. If you've seen natural Ultem, you know what it looks like. It has kind of a tint, an amber tint. It's getting lighter as the years go on, but it's still far from a water clear material like polycarbonate. And this was 20 years ago when the color was a lot darker than it is today, and the desired color on the part of the customer was white. What we found was that in order to achieve the desired shade of white, we had to put in 9% titanium dioxide. The desired levels are around 1 to 3%. At 9%, we're no longer talking about a color, we're a lot more talking about a filler. And so obviously when you put 9% of anything into a base resin, you're going to alter the balance of load-bearing properties and impact performance that are in the base polymer. So loading considerations are key. While colorants impart desirable appearance, they still represent contaminants. And so low loadings are desirable. We want to try and keep the level of colorant to a minimum in order to achieve the appearance we want to see. Anytime we go to higher loadings of any colorant, we run the risk of interfering with performance. And usually the first property to run into problems is that of impact resistance. Best results are achieved with levels of about 1 to 2%, if that's achievable. Now, potential property changes, I already mentioned impact, and impact is one of the main things we're concerned about, and we'll show some examples of where that's happened. In a semi-crystalline material, one of the things we run into is that the colorants very often can influence the crystallization rate of the material. And if you influence the crystallization rate of the material, you're going to change things like the cycle time. You're going to change the shrinkage of the material, which influences dimensions, which influences the potential for warpage. If you'll notice, when you go to UL's website and look at their yellow cards, you'll notice the very first column on the left-hand side of the yellow card is the word color. Color is linked to the ratings that are provided by UL, especially for flammability. And so very often, the notation under color will say all. which basically means they've looked at enough colors to where they're satisfied that whatever you throw in this material, they're happy with the fact that the flammability rating they provided will hold. However, very often you'll see it just says black, or it just says natural, or it may say natural, black, and red. And so what this basically tells us is that color is important to even things like flammability ratings, and there's a recognition that changing the color package can change this rating. And then, of course, UV stability. There are certain colorants that are natural UV stabilizers or UV screens. Carbon black is probably the best known, and very often the easiest way of stabilizing a material against UV is just to put enough carbon black in. 2% is usually the number that's quoted. If you work with PVC, you know that if you're going to use PVC outdoors for extended periods of time, and you don't want the color to shift and the material to become brittle, you need to have a certain amount of TiO2 in the material, and that number typically is quoted as 3%. More than 3%, you get good results long term. Less than 3%, you get color shift toward brown, and you eventually get embrittlement. So there are some natural protections that some colors provide, but not all. When we talk about the hazardous substances, the first exposure we typically had to this was the RoHS, the Regulation of Hazardous Substances, which focused primarily on what we usually call heavy metals. And the ones that people are most familiar with, cadmium, lead, mercury, tetravalent chromium. Cadmium and lead were very, very important in pigment systems for reds, oranges, yellows, things of that sort. And we used these materials because they worked. It wasn't like we were trying to destroy the environment by putting these materials into our plastics. They were efficient systems. They were very thermally stable, so they were very forgiving when it came to processing. They were often more stable than the polymer into which they were placed. They often provided secondary benefits, such as weatherability. And all of a sudden, they're going away because of the need or the perceived need to have these materials out of our environment. Replacement systems can exhibit reductions in thermal stability and can also influence impact performance. And if you've been through this process of conversion from a heavy metal-based pigment to a heavy metal-free pigment, you know that sometimes it can be very easy and sometimes it can be very, very challenging. Here is a case study of something I was personally involved in converting a red colorant for nylon from a cadmium-based system to a cadmium-free system. Now, we had done this conversion in polycarbonate. It was very straightforward. We did it on the first pass. There was no sacrifices in performance, no sacrifices in processability, and everybody was happy. We did the same thing in a general purpose glass-filled nylon, and that conversion was seamless. And then we took the same technology and put it into an impact-modified glass-filled nylon, and we lost all of our impact resistance for reasons that we never really determined. A lot of times these mechanisms remain a mystery because no one has the time to really dig into the root causes. But the bottom line is this is an application that required very good impact, which is why we were using an impact-modified material in the first place. And when we put this red color in, we lost all that impact strength. It took 4 more generations of red color matches and attempts to match before we had the combination of color match, thermal stability in processing, and performance in the end use that was desired in order to get us back even close to where we had started from when we started out with the heavy metal system that we've been using through the 70s and 80s and early 90s. So these are just the kinds of things that come up in the real world that we have to contend with. Putting color into a plastic is not simple necessarily. Another example where we have interactions between a pigment and an additive in the material. This is a white polycarbonate that was being manufactured with a V2 flammability related polycarbonate. And the material, the base resin, was changed to a V0 rated material, which means it's got a little more flame retardant in it. Not a great deal more, but a little bit more. What we discovered as we got into the new material was the new material was very sensitive to pigment loading. And if we got pigment loadings of TiO2 higher than 2%, we started to see reductions in impact strength. And the way we ran into this is we got a batch of resin in from the compounder. These were fully compounded material, so there's no color concentrate being used. Everything's coming in, it's all white. And we started to mold the material, and we started noticing notch sensitivity in a particular part. And when we did the pigment analysis, we found we had nearly 4% pigment in the bad batch. We looked at a good batch, and we had 2%. And we thought, well, this is kind of strange that we have this much variation, but if this is typical variation from the compounder, why weren't we seeing the problem in the old material? When we do notched izod tests on the old material versus the new material, this is what we run into. We run into a situation where 5 out of 6 specimens might look good, but we get that one specimen that shows a brittle failure. And when we went back and looked at this in an orchestrated way, prepared batches of material with controlled levels of pigment, this is what we saw. The old material was insensitive to the pigment loading. So the problem with control over pigment had always been there. But now we have a new material, and the consequences of losing control over pigment loading become a lot more severe. And this was due to an interaction between the flame retardant that was being used in the polycarbonate and the white pigment that was being incorporated into the material. TiO2 is a relatively harmless pigment system in polycarbonate, provided that the pigment system is properly prepared chemically. There's a lot of papers out there about TiO2 degrading polycarbonate. But the real reason for that has to do with the chemistry of the TiO2, and I'm not going to get into that because there isn't enough time. There's some good papers on that. You can research that yourself. But a properly passivated TiO2 going into polycarbonate shouldn't cause problems for the material. But in this case it did, not so much because of the ingredient, but because of the amount of the ingredient that was being put in. Now in semi-crystalline materials, as I mentioned, the colorant has the ability to change the way the material crystallizes. A lot of these pigment systems act as nucleating agents for materials like polypropylene and polyethylene. And when you nucleate a material, you change its crystal structure, and therefore you change its properties. In this case, the blue material that we were using, and it was a concentrate in this case, we noticed one thing, it resulted in a significant reduction in cycle time. And when we did the analysis in the lab, the reason for this became very clear. It also changed the size of our critical dimensions. And if you ever molded close tolerance parts in a material like polypropylene, and you've changed colors, you know that this is what happens. You know that you have to make processing adjustments sometimes as you go from green to black, for example, because all of a sudden the parts are coming out a different size. And the reason they're coming out a different size is because the two pigments are interacting differently with the base resin in terms of how the material crystallizes. The thing that we really noticed that was of great concern to us was that we saw a marked reduction in impact performance when we used the blue colorant in the polypropylene that we were coloring. Now, this is an analysis we performed in the lab to understand what was going on between an uncolored polypropylene and the blue. And read this graph from right to left. Okay, so we're cooling the material from the melt, and as the material starts to solidify, we get this big spike in the trace, and that spike represents the heat release associated with crystallization. So we can actually see the material crystallizing in our instrumentation. Now you'll notice that the blue material crystallizes much earlier. And what that translates to is a much faster cycle time. We can open the mold a lot quicker because by the time the natural material has started to crystallize, started to solidify, the blue material is already done. So from a cycle time standpoint, this is great news. And we certainly try to capitalize on this. It also has an influence on the way a part shrinks. But the bad news is it also brings with it a sacrifice in performance. When we do falling dart impact strength tests on the material, we find that the blue material is brittle and the energy required to break the specimens has dropped by 80%. So this is obviously an unacceptable condition, and we need to go find a different way of making the blue color that we want, because this particular blue pigment system is not doing what we want it to do. It's giving us a nice looking part, and we maybe can figure out how to change the process in order to get the dimensions to come back in, but the performance of the product is not there for the end user. And if you do a lot of work in polyethylene and polypropylene, and you do a lot of colors, you will have seen some of this, I'm quite sure. You also will have seen certain colors perhaps tend to produce a greater degree of warpage, or a greater degree of shrinkage. And this is all due to this interaction between the chemistry of the color system and the chemistry of the polymer. This is another example. This is a green colorant in a high-density polyethylene, and once again, by looking at the way the material cools, we can understand something about the influence that the colorant system is having on the polymer. This is the natural polyethylene, and you can see the peak temperature of recrystallization at 109 degrees C, and we put in the green color, and that jumps up to 116 degrees C. That may not seem like a lot, 7 degrees C. Trust me, it translates to a lot. It changes the cycle time a great deal, and it changes the performance of the material by a great deal. And it's gotten to the point now where when I work with a customer on a problem and color is an aspect of the formulation, the first thing I ask them, and it sounds like a stupid question, but you'd be surprised how often the answer is yes. The first question I ask is, can you take the color out and will everybody still be happy? And a lot of times people say, yeah, this is just something that somebody designed and they thought would look nice if it was green or blue or red, but we really don't need it to be that color. And so one way of simplifying a failure analysis matrix is get rid of the color, because it is something that adds to the complexity of the situation. Now, in putting color in, there's some considerations in terms of how we go about it. And the first of these is that the colorant chemistry itself has to be compatible with the polymer. And as I mentioned before, there's a lot of good literature out there about what colorant systems should not be put into what polymers, and I won't go into that specifically. There's a lot of good information out there about that. The other decision point is, how are you going to put the color in? How are you going to incorporate it? And the big decision point is usually the debate between buying a fully compounded material, where an extruder or compounder has done the work of putting the color in and evenly distributing it through the matrix, as opposed to buying a color concentrate or a liquid color or a dry color, if you like, and incorporating it into the material at the point where the process of making the parts is being conducted, the so-called coloring at the press strategy. And this is a big debate. People go back and forth on this about what's the more effective way to do it. If you're going to use color concentrates specifically, concentrates use a carrier resin to bind the color. And so the big concerns with concentrates are twofold. Number one, the carrier resin needs to be compatible with the base resin. And number two, the molecular weight of the carrier should be properly matched to the base resin. And these are things that are very often overlooked or are intentionally ignored, either because of some misconceptions about what's needed technologically, or simply because people are trying to save money. Now, from an economic standpoint, color concentrates provide a lower cost route, provided that you can control the molding process and the mixing process, and you have equipment that is suited for properly mixing the color into the base resin so that you don't see swirls and non-uniformities. And this is a common problem, and a lot of this relates not so much to the color concentrates themselves, but to the equipment that is running in our machines. If you talk to people who do extrusion, they'll look at your injection screws and kind of just shake their heads and say, well, it's no wonder you're having mixing problems. General purpose screws don't really do a very good job of mixing. And there's a lot of good technology out there to enhance mixing if you're willing to go out and experiment with what we call mixing screws. And very often, if you're going to color, especially high viscosity materials like polycarbonate, you're going to need to get into those kinds of technologies in order to be successful. Having said that, there's a lot of incentive for doing the color concentrate route. Number one, turnaround times on color concentrates are a lot shorter than on specialty colors of fully compounded material. Minimum order quantities are also much smaller. You can buy 25 or 50 pounds of color concentrate. A lot of times minimum order quantities on a specialty color are 1,500, 2,000, 3,000 pounds, and a lot of people complain about the fact that they're having to buy, a 7-year supply of resin in order just to get the color. And obviously that's not very economical. The other thing about color concentrates is you don't commit to the color of the resin until it's time to make the parts. So you're not trying to guess about whether or not the hot color of the month that's going to sell a lot is turquoise or burnt orange, and you have to go out and buy a lot of pre-colored turquoise. And then of course, when it doesn't sell, you've got a lot of turquoise sitting in the back, taking up space and costing you money in terms of inventory. One of the first jobs I had in this industry was to go back in the warehouse where I was working when I was brand new and clean out all the old obsolete colors of ABS that we've been using to make telephone handsets for the residential phone market back in the mid-70s and early 80s, back when we used to have telephones that hung on a wall or sat on a desk, and all the stuff was made of ABS. And a lot of the colors that were big sellers at one time fell into disuse, fell out of favor, and there were 45,000 pounds of obsolete ABS colors sitting in the back of the warehouse that had to just be thrown away. So obviously that's not a smart way to spend your money. Now, some problems with color concentrates, incompatible carrier resins, and this is a universal issue. This is not just from the people who make color concentrates for a living. This is also, and I'll show you in a minute, sometimes it actually comes even from the base resin manufacturers that supply salt and pepper mixtures. If you're going to color nylon, your color concentrate should be based on nylon, not polyethylene, not polypropylene, not EVA. We've already said color is a contaminant. So it's bad enough that we're putting in 1 or 2% color as a contaminant. The last thing we want to do is double up on that contaminant by now putting in an incompatible carrier as well. Now the excuse usually is, well, you know, it's only a couple percent, so we'll get by. And that may be true. But I've seen a number of cases where it actually does hurt the properties enough to make the difference between a good part and a bad part. And if nothing else, it can also cause problems with processing. There is no such thing as a universal carrier. Let me be very clear about that. If there were, we could mix polymers together a lot more freely than we do, and if somebody dumped ABS in your polycarbonate, it wouldn't turn into delaminated mica in your molding machine. Most polymers do not like to mix. Very few combinations mix well. And when you put polyethylene into almost anything else besides polyethylene or an ethylene-based copolymer or polypropylene, you have incompatibility. The other problem we're running into, and we're seeing this more and more, is proper selection of carrier resin, but the molecular weight is too low. So we're coloring polycarbonate, and we're using polycarbonate as a carrier resin, but the melt flow rate of our base resin is 10, and the melt flow rate of our carrier resin is 140. All this does is introduce a low molecular weight tail into the material, and it reduces properties, and it also reduces process stability. And I've got a couple of case studies to show you to back that up. Now this is Nylon 6.6. This is a case study on 6.6. This is a salt and pepper mixture coming from a major supplier of nylon. Now when you open up a bag of nylon and it's got the name of a major supplier on it, you kind of assume that what's inside has been vetted by some pretty smart people. And this has got a black concentrate inside it, mixed in with the base resin. What we found as we struggled to mold this material, because we were having problems with cosmetics of the part, we were having problems with screw slippage, was that the concentrate was based on ethylene vinyl acetate, EVA. Now, if you've worked with EVA, you know that it has some upper limits, as all polymers do, in terms of when it starts to decompose thermally. And unfortunately, it starts to decompose thermally at temperatures at which you typically would mold nylon 6.6. And this decomposition produces a wax, and the wax is what produces the screw slippage and the nasty-looking appearance on the part. And after realizing we were dealing with this contaminant, we went to the supplier and said, we'd like you to change the formulation of the concentrate. And they said, no, we can't do that because we have to do this in order to keep costs down. So we said, well, in the future then, send us natural material. We'll take care of coloring it ourselves. We went out and bought a color concentrate based on nylon 6, and that solved the problems. The low molecular weight carriers. This is being done ostensibly in order to improve mixing. Now, it is true that matching viscosities of your colorant and your base resin is important in order to optimize mixing. You don't necessarily want to have them be the same, but if you get them too far apart, it actually is counterproductive. And so I see a lot of strategies for concentrate use that just simply do not make a lot of sense, and I'll show you an example of that in just a minute. This is a green polycarbonate being molded in a 20 melt flow rate base resin with a green concentrate. We're getting brittle failures in the part, and whenever we get brittle failures and we look at doing a failure analysis, one of the things that's always on the table is molecular weight, because losses in molecular weight produce losses in performance. And the easiest way to measure molecular weight is to measure melt flow rate. So we measure the melt flow rate of the virgin resin, and we measure the melt flow rate of the molded parts. If you're used to seeing these numbers, you know that the left-hand column and the right-hand column present very, very bad results. You do not want to see this kind of change between raw material and molded parts. And the initial presumption was, oh my God, the molding process is doing horrible things to the base resin. I have learned when color concentrates are involved, don't be too quick to point the finger at the molder. It may not be the molding process at all, and in this case it certainly was not. When we got a sample of the colorant and we ran the colorant pure through the melt flow rate tester, you can see what we saw. Not only is the colorant melt flow rate rather high, but the colorant is unstable. These measurements are made 15 seconds apart on a single sample weighing about 3 grams. And the material is a moving target. It starts out looking okay, and a minute later, the melt flow rate has gone from high 40s to low 80s. That's a very, very bad sign. And some of that instability has actually been communicated to the molded parts by virtue of the fact that the concentrate is being mixed in with the base resin. So the color concentrate is definitely a component of the problem. When we remove the colorant and we try again on the molding process with nothing changed in the molding conditions, different batch of resin, so you can see the melt flow rate's a little lower now. That's just lot-to-lot variation, no big deal there. We now go from 18 grams per minute to 21 grams per minute, which is a very acceptable change in melt flow rate. The molding process is not the issue, the color concentrate is the issue. And this is the kind of thing that we're running into more and more. And it's important for people who are doing the formulations of color concentrates to understand that there is an upper limit on the melt flow rate of these concentrates. And when you start introducing materials with melt flow rates of 100, 150 into base resins with melt flow rates of 10 and 20, you are doing nothing but making life miserable for everybody down the line. Here's a second case study. This is also polycarbonate. We were looking at melt flow rates that were excessive in the molded parts. The way this first showed up is parts that are warranted to last a minimum 3 years are cracking in the field in a period of anywhere from 3 to 6 months. So we bring the parts back in, we do melt flow rate tests, we compare the colored resin, which is a natural plus color concentrate, to the molded parts, and regardless of which color we look at, you can see significant changes in melt flow rate. These are associated with unacceptable reductions in molecular weight, so not a big surprise that we're running into problems with performance in the field. When we go in and look at the molding process, we see some obvious issues with drying. And if you've run polycarbonate before, you know that drying is a very, very important component of property retention. And so we get the drying problem solved. We go back and revisit the process, and we can see that we've made significant improvements. But once we get the drying issue taken care of, now the colorant stands alone as a factor, and it starts to show up as a second issue. And you can see that in this data here. The natural resin compared to the natural part, you can see the change in melt flow rate. It's only about 12%, which is a very acceptable change. Using the same process, but now having introduced the blue colorant, we now see a shift of about 30%. Now that's still acceptable, but the problem we ran into is, and this is kind of ironic, but once the material started to be dried properly, the viscosity went up. This is also something you'll see. Viscosity goes up as the moisture content goes down. So the molder started having trouble filling the parts. So they had to raise the temperature of the material in order to compensate for that increase in viscosity that resulted from the lower moisture content. Now the change they made is a perfectly acceptable change for most polycarbonates. 288C is about 550 Fahrenheit, 303C is a little shy of 580. Polycarbonates should be able to stand that change. And although the data is not here in this table, the natural material had no trouble with that increase in temperature. But the blue material showed a significant shift in the melt flow rate, and now we're actually back into an area where we have concerns about the integrity of the material. When we sampled the concentrate by itself, we found the melt flow rate of the concentrate was 90. There's no reason in the world to have a melt flow rate of 90 for that color concentrate. Something on the order of 30 would be perfectly fine and would make for a much better product in the long run. These are things that we're running into on an increasing basis, and whenever color is involved now and someone says, yeah, we're using a color concentrate, that becomes a focus of the investigation because we see this so often. So it's just a summary of what I just went through. So to conclude, molded in color represents a major benefit of plastics over metals and other materials that require painting. We know this. We utilize it all the time. We're trying to drive more and more toward this advantage, even in areas where we traditionally have painted, such as automotive and such as large equipment panels and things of that sort. When done correctly, either with concentrates or liquid or dry color, if you like, or fully compounded, the properties of the materials can at least approximate, if not equal, those of the base resin. But coloring, like everything else we do in this business, is a science. And it has principles that must be adhered to in order to achieve optimal results. We've highlighted some of those today. Hopefully this has been of some assistance. It's made you think a little bit perhaps about some things that don't get a lot of attention on a day-to-day basis. And with that, I'm going to conclude my presentation, and hopefully we have a little time for Q&A. So Jake, I'm passing it back to you.
Yes, looks like we got a question here. I've heard the statement that red is just hard to process. What does that mean?
Well, that can be true depending upon how the red is being achieved. The red I was referring to specifically was a cadmium-free red system in a nylon. Now, the way the difficulty in processing manifested initially actually wasn't processing, it was performance of the part. As I mentioned, we lost our impact strength on an impact-modified material. The reformulation gave us processing issues because the thermal stability of the colorant chemistry was limited, so much so that the temperatures we needed to use and the shear rates we needed to use to process the nylon were actually causing the colorant system to degrade. And the way this manifested was we saw darkened streaks in our parts. The red actually started to turn brown. And this was from the thermal degradation of the pigment, not from the nylon. You know, a lot of people say, well, the nylon is turning brown. But when we ran natural nylon with the same process, we saw no discoloration. So we knew it was the colorant system. And this is, always the challenge. If you run high heat materials, if you run really high heat materials like polyether sulfones or PEEK or things like that, and you have colors other than black and natural, you probably have experienced this at some point in the past. If you haven't, then your colorant supplier is doing a very, very good job, because they have to be aware of the fact that these colorant systems are going to be exposed, if only briefly, to temperatures many times upwards of 700 degrees Fahrenheit. And not every colorant system can do that. And if the colorant system cannot survive the molding process, then it's not something that you can use. So difficulty in processing very often is defined in terms of, how well does the color survive the molding conditions, and that's what I'm referring to.
Okay, and I got another one here for you. Let's see here. How does using color concentrate affect flame ratings?
Well, there again, that depends an awful lot on the two things we talked about. It depends upon the carrier resin and whether or not it's compatible, or whether or not it has the potential to change the way the material is going to respond to the flame test. So, just imagine a situation where you have a, let's say, a flame retardant glass-filled PBT, and someone puts a concentrate in that that utilizes polyethylene. Now, polyethylene, as most people know, is not flame retardant. To make polyethylene flame retardant requires a significant amount of modification of the material. So, polyethylene, to be polite, is basically like high molecular weight gasoline. So the more polyethylene you put into the material, the more likely you are to shift the flame rating. And of course, a lot depends upon the letdown ratio of the concentrate, something we didn't talk about. Now, letdown ratios are usually 3, 4, 5 pounds per 100, but I know people who are using 10 pounds per 100 in order to get better incorporation of their color into the base resin. So that means they're using more carrier resin than they typically would. So if that carrier resin is not compatible, and if it's a material that is a little more prone to burning than the resin they're putting it into, it can shift. So normally, when you do color concentrates, you have to go, and you have a UL approved part, you have to go through an approval process with UL so that UL is satisfied that the colorant that you're using and the way you're using the color is not compromising the rating that they've published for the base resin. And it's a lot of work, but in many cases it can still be worthwhile.
Okay, and I got one more here for you. Do you have some case studies on medical applications for color concentrate? How much percentage of color is best?
Well, you know, again, when you talk about medical now, you're talking about a whole range of potential concerns. You could be talking about simple property profile retention, such as impact performance, such as load-bearing properties, but you could also be talking about things like biocompatibility. So it really does depend, first of all, upon which property or which performance characteristic you're talking about. In general, the rule of thumb is the less you have to use, the better. But anytime you put a color into a base resin and you're going to use it in a medical application, depending upon where in the medical field it's going to go, you have to go through whatever the appropriate approval processes are. If it's going to be an implant, obviously, that's good. A different set of concerns. And if it's going to be a little connector in a tube set that's going to conduct contrast fluid or something of that sort. So not an easy question to answer without some more specifics on exactly what you're doing. But I will say this, in most cases when you have a product going in medical device and you have multiple colors, the rule of thumb is every color has to be qualified simply for that reason. Because anytime you change up the color system, you're potentially changing up the key performance parameters that are important to that application. Great.
And then got one last question for you here, and this is, we are using liquid color on an ABS application with swirls resulting. The screw has a longer transition zone with a mixing head. You mentioned concentrate. You mentioned low MW carries in concentrates. Are there similar issues to look at with liquid color?
Yeah, there are. Now, for the most part, what I've observed, and I've not used a lot of liquid myself. I did some experimenting with liquids early on back in the mid-'80s. We did head-up comparisons between liquid and color concentrate, and this is a long, long time ago. And we actually felt that concentrates were more workable. Not only did we not have to invest in the pumps and the handling equipment for the liquid, but we actually did see better incorporation, which means fewer swirls when we use color concentrate than we did when we used liquid. And some of the people I was working with who were also running the same experiments had the same experience. Now, again, this goes back a long way. People I know today who are using liquid are having very good success with incorporation. And I think that's just a representative of the fact that liquid coloring has come a long way. But viscosity matching is still an important issue. And so, different liquid color suppliers perhaps bring a different skill set to the problem. And so you might find that two different suppliers of liquid would provide you with very different performance in your application. But if you're seeing swirls and you've taken the time to actually create mixing elements within your screw, then it would be good to evaluate the role of viscosity matching in the process.
Great. Well, as far as questions go, ones that haven't been answered, you can see Michael's contact information is listed there below. And so if you'd like to reach out and have him answer those questions for you, there's his contact information. And we'd like to thank Michael for presenting today, and thank you all for attending today's webinar. And thanks again, and have a great day.